All right, today we're looking at graphing rational functions that are a little bit more complicated. But before we get into that, we're going to revisit how we graph rational functions using transformations. So in this first example here, I want to first revisit what the parent function is, y equals 1 over x. So if I make a table of inputs and outputs, I'm going to go from -3 to +3. My outputs then are -1/3, -1/2, -1. 0 on the bottom of a fraction is undefined. 1, 1/2, 1/3. Okay, if I look through the transformations, the 2 is a vertical stretch by a factor of 2, 3 units to the right, 1 up. Okay, so let's graph our asymptotes. So 3 to the right, so right here, that's my vertical asymptote at x equals 3. Okay, my horizontal 1 up, so right about here at y equals 1. Okay, if I plot my parent function first, if I go to where the asymptotes cross right there, that's like my makeshift origin. So I would go over 1, up 1. And then as I go over 2 and up 1/2, I can also go over 1/2 and up 2. Okay, over 3, up 1/3. So over 1/3 and up 3. And I can do the same thing in this region. So over 1, down 1, over 2, down 1/2. So over 1/2, down 2. That's what makes it a reciprocal function. Over 3, down 1/3, over 1/3 and down 3. So those are my parent points, but I still need to stretch it vertically. So if I start with this first point, I'm 3 away from the asymptote. I need to double it, so I need to be 6 away. Okay, 2 away becomes 4 away. 1 away becomes 2. Half becomes 1. 1/3 becomes 2/3. And here is my first branch in purple. Okay, same thing over here. Okay, if I'm 3 away, now I need to be 6 away. 2 doubles to 4. 1 to 2. Half to 1. 1/3 to 2/3 away. All right, there's my final draft in purple. My domain, really anything except for where I have an x value of 3. So -∞ to 3, union 3 to infinity. Okay, my range, really anywhere except for where y is 1. So -∞ to 1, union 1 to infinity. My horizontal asymptote here, right, is y equals 1. My vertical asymptote here, x equals 3. Okay, next I'm saying, can you rewrite this function in transformation form? So here we have to use long division. So I'm taking this x minus 3, and I'm trying to divide it out of x minus 1. I like to build my structure, so parentheses, there's my subtraction, and then I'm thinking, well, x times what is x? Well, just 1. Multiply the 1 back over the x and the minus 3, so I have x minus 3. So now x minus x is 0. -1 minus a -3, right? That's like plus 3 is just 2. So when I rewrite this, I have g of x equals here 1, right? It divided in 1 time, plus 2 that's left over, out of x minus 3. And then we typically rewrite it, g of x equals 2 over x minus 3 plus 1. Okay, hope you can see what I did just there. I really just derived the same function as the one we graphed. We're just seeing it in a different format, but ultimately it is the same function. Okay, now that's a good segue into this more complicated variation. So here, let me slide this up. I'm giving you one example, and I'm going to use this problem throughout. So when I look at this problem here, what I recognize is that this is a rational function. It's a polynomial over a polynomial, but I don't see it in that transformation structure, right? This is just a polynomial. It could have any number of terms over another polynomial. Okay. We recognize that we have this domain restriction for any rational function. We know that the denominator of a quotient, fancy word for fraction, can't be 0 or it's undefined. So x cannot be any value that makes the bottom of the fraction 0. When we start to graph these, we're going to see that those domain restrictions are going to show up graphically as vertical asymptotes or holes. So here first, let's address the vertical asymptote or asymptotes. In this class, we only have you graph ones that have a singular vertical asymptote, but you could have problems that have more than one vertical asymptote. We know it's going to be a vertical asymptote when we have something that's left behind in the denominator. So here's my original function. I'm showing you how we're factoring it out. And when I get to this stage, I see that I have a common factor on top that's also on bottom. So I can reduce it down. I know that anything over itself is just 1. So then it simplifies here to be negative times parentheses x plus 2 over x plus 4. So that x plus 4 is what's left behind. That's going to give me a vertical asymptote. I just set that x plus 4 equal to 0, and I solve. And I get that x equals negative 4. That's going to be a vertical asymptote. Okay, next, a hole. So a hole or holes plural, you could have more than one. It's what cancels out of the denominator. It's a hollow point on the graph. And to find its specific location, we plug in the x to get the y. It's going to be a hollow dot on your graph. So again, I'm showing you the same original function. I'm showing you it factored down just to save some time. And I see that it's the x minus 2's that cancel away. That's where my hole comes from, right here. So x minus 2 equals 0. Add the 2. X equals 2. That's the x value of my hole, but I need to find its y value, so I plug in x to get the y. And when I do that, I'm always doing it in this reduced format. So my y value is going to be negative 1, right? Again, I'm plugging in right here. So negative 1 times 2 plus 2 over 2 plus 4. So on top, I have negative 4 over 6, which is negative 2/3. So my hole as a location is at 2 comma negative 2/3. Always write it as an ordered pair. Horizontal asymptotes, we have 3 types. It's really contingent on, is it top heavy? Top heavy means you have a higher degree on top. I see that I have something cubic over something quadratic. And when it's top heavy, we don't have a horizontal asymptote. None. Okay, bottom heavy, I have a bigger degree on bottom. So in this example, I'm giving you something that is quadratic over something cubic. So bigger exponent on the bottom. Whenever that happens, it's going to be at y equals 0. Okay, when it's same degree, like our example, this is our example, we're looking at the leading coefficients. So it's always going to be y equals, then we divide those leading coefficients. Okay, so in our example, I'm looking at that -1 over 1. So y equals -1 over 1, which is -1. Y equals -1. That's what it's going to be for our problem. Okay, then we also need the intercepts. I want the x-intercept and the y-intercept. So the x-intercept right here, we know that we plug in 0, we solve for y. So here I'm showing you that when we factored it down, we got from this original to this reduced version. Okay, so now if I'm saying that 0 equals -1 times x plus 2 over x plus 4, and I'm trying to solve for x, I would first clear my fraction. I multiply each side of my equation by x plus 4. So what happens on the left-hand side? I'm multiplying by 0, so this whole side becomes 0. And over here, those x plus 4s cancel away 1 to 1. So I'm left with -1 times x plus 2, like that. And if I divide away the -1, I have 0 equals x plus 2. I want you to see that really clearly for a moment, that what I really have is whatever the factor is on top set equal to 0. That's always what it's going to be. So now when I take away the 2, I get that x equals -2, again, when y is 0. So I'm going to have a point at -2, 0. That's my x-intercept. Okay, lastly, I need the y-intercept, and then I'm going to put all this on the graph. So my y-intercept, again, I'm showing you first my original function and then the reduced version. So I'm always plugging into this reduced version, and I want to plug in 0 and solve for y. So here I have y equals -1 times 0 plus 2 over 0 plus 4. So I get -2 over 4, which is -1/2. Y is -1/2, of course, when x is 0. So as a point, 0, -1/2. All right, so then how do we graph this thing? So let me zoom out a little bit so we can see all these pieces together. Okay, so let's start with the vertical asymptote and the horizontal asymptote. I know that that vertical asymptote is at x equals -4. So right here is my vertical asymptote. Okay, the horizontal, y equals, divide the leading coefficients. That was y equals -1. All right, so my asymptotes are in place. So next thing that I'm looking at is where my hole is. So my hole is at 2, -2/3. So I'm over 2, down, -2/3. So hollow dot right there. Now, if I want to plot another point, remember how to mirror it. So if I think about how I got there from where my asymptotes cross, I went over 6, and that would really be up 1/3. So I want to go left 6 and down 1/3. That's another point where I'm going to have a branch over in this region. All right, next I have my x-intercept. Let me slide this up. My x-intercept is at -2, 0, so right here. Okay, now if I want to mirror that, so went over 2, up 1 from where my asymptotes cross. So I want to go left 2 and down 1. It's going to give me another point. Okay, lastly, the y-intercept. Here I have 0, -1/2, so right here. Again, go to where those asymptotes cross. That's going over 4 and up 1/2. So I want to go left 4 and down 1/2. So those are the points we want to see. We want 6 points total, and it just helps you to smooth out the curve for your 2 branches. And again, you want to hug those asymptotes just like so. All right, let's do it again. Flip it over. Okay, so here, same idea, and I'll keep it zoomed in as close as I can so we can see all the things. Okay, so find each of the following features, they're all listed, and then graph it, include at least 6 marked points. So my first thing I have to do is factor this down. So divide out a -1, leaving behind an x plus 2. Okay, on the bottom, if I factor this down, that becomes x minus 3 times x plus 2. I can see that the x plus 2's will cancel away 1 to 1. So I get -1 over x minus 3. Okay, so my vertical asymptote or asymptotes, in our examples, we're going to see only one. It comes from what is left behind. So when I set that equal to 0, the x minus 3 equal to 0, and solve, I'll get a vertical asymptote at x equals 3. Okay, my whole or wholes come from what cancel away. So if I set x plus 2 equal to 0 and solve, I get a whole at x equals -2. But I need to plug in to find the y value that goes with it. So I plug into this reduced format. So -1 over -2 minus 3. So I get -1 over -5, which is just 1 over 5. Okay, as a point, I'd say -2 comma 1/5. Okay, horizontal asymptote, let me slide up. It is bottom heavy. I have a bigger degree on bottom. I have a linear over a quadratic. Bigger exponent on the bottom, bottom heavy. So that tells me it's going to be at y equals 0. Okay, x-intercept, that's when y equals 0. All right, so I want you to just think about this for a minute. If I have a horizontal asymptote right here, will I cross through the x-axis? No. So here, make a little note. If a function is bottom heavy, it can't have an x-intercept. Right, so we would say none. And let's say that I forgot about that and I tried to solve. Watch what would happen, right? I would take this right here, my reduced form, set it equal to 0. So I would have 0 equals -1 over x minus 3. If I clear that x minus 3 from both sides, I'm going to have 0 equals -1, right? I can't solve that. So that just confirms I don't have an x-intercept. Okay, my y-intercept, that is when x equals 0. So if I plug into my reduced format, y equals -1 over 0 minus 3. So -1 over -3 is 1/3. So as a point, 0, 1/3. Okay, there we go. So now I'm going to start the graphing process. Let me slide to there. So my vertical asymptote is at x equals 3. Okay, my horizontal asymptote is at y equals 0. All right, my whole is at -2, 1/5. So right here, a little hollow dot as close as I can get it, right? That's supposed to be 1/5 up. So again, if I want to mirror it, go to where the asymptotes cross. That was left 5, up 1/5. So I want to be right 5, down 1/5. So right about there. Okay. Then I also, let's see, I don't have an x-intercept. I do have a y-intercept, so I'll use that point. So 0, 1/3, so about here. So again, go to where the asymptotes cross. Left 3, up 1/3, so right 3, down 1/3, right here. Ooh, but I like having just one more point. So let me slide this up for a minute. So here's where my vertical asymptote is. Let's say that I use x equals 2 for my one more point. Okay, so I use x, I use the x value that is one left of where the asymptote is. So go back to that reduced function right here. Plug in for x, y equals -1 over 2 minus 3. So -1 over -1 is just 1. So this gives me one more point here to the left of that vertical asymptote, 2, 1. So from where they cross, I'm left 1, up 1. So my other point will be right 1, down 1 to mirror. Okay, and then I make my first branch. Looks like that. And my second one looks like that, right? I'm hugging my asymptotes. All right, let's do it one more time. All right, so here again, I see my function. It looks a little bit more complicated. I see a polynomial over a polynomial. So I first have to factor this out. Okay, on top, I can see that it has to be 2x and x. And I see here that I gotta have it has to multiply to 3 here to here. And I know that it has to be a -7x in the middle. So they both have to be negatives. It's just a matter of which one is the 3 and which one is the 1. So if I put the 3 here, let's check that out. Here, I would have -6x and the 1 here, -1x. That would get me the -7x in the middle, so that is fully factored. Bottom is a difference of 2 squares, x minus 3 times x plus 3. So we can see that we can cancel out the x minus 3's, 1 to 1. Reduced down, I have 2x minus 1 over x plus 3. All right, vertical asymptote. What got left behind on the bottom? The x plus 3. Set it equal to 0 and solve. X equals -3. Whole. What canceled away? Right here. The x minus 3. Set that equal to 0 and solve. We have a whole at x equals 3. But I still have to find its location. So I need to plug that 3 into this reduced format right here. Y equals 2 times 3 minus 1 over 3 plus 3. So 6 minus 1 is 5 over 6. So y is 5, 6. My whole as a point is 3, 5, 6. Okay, my horizontal asymptote, I see that it's the same degree. It's a quadratic over a quadratic. So I divide the leading coefficients. So 2 divided by 1, right, is just 2. Y equals 2 is the equation. Okay, my x-intercept, we've seen this a few times now. We should know that it comes from the factor on top. Okay, so I know that y is 0. The factor on top is 2x minus 1. So 0 equals 2x minus 1. Add the 1. Divide by 2. And x is 1/2. X is 1/2 when the y value is 0. Okay, and then lastly, the y-intercept, right? X is 0. So I'm still plugging into that reduced format right here. So y equals 2 times 0 minus 1 over 0 plus 3. So -1 over 3. So when x is 0, y is -1/3. All right, we have all the information we need. So now graph the asymptotes. So x equals -3 is the vertical asymptote. Y equals 2 is the horizontal asymptote. Okay, look for the hole next. Here's my hole. So 3 and 5/6 up. So right about there. I'm always making that hole hollow. But I want to plot that point mirrored over here. So I go to where the asymptotes cross. Right? I can see that I went right 1, 2, 3, 4, 5, 6, and down 1 and a 1/6. So I want to go 6 left and up 1 and a 1/6. So right about there. Okay, then my x-intercept is at 1/2, 0, right there. Okay, to get there, went right 3.5 and down 2. So I want to go left 3.5 and up 2, right there. Okay, and then lastly, I have 0, -1/3, so right about here. To get there, went right 3 and down 2 1/3. So I want to go left 3 and up 2 1/3. So right about there. Okay, I have 3 points on each side of my asymptote. I can go ahead and connect the dots. If you ever want more information, you could always pick an x value to the left of the vertical asymptote and then mirror it on the right or vice versa. All right, that's our lesson today. We will circle back next time we see you. Have a good day.